Okay, so today we'll continue worksheet 18. We'll do number 3, 4, and 5, and 6. So let's look at number 3 from worksheet 18. Please read the question and see if you can think of a way to solve this. So the basic idea is similar to the linear motion. Usually when we solve this kind of problem, we come across 5 different physical quantities. They are like in linear motion. If you remember, in linear motion we have position, displacement, velocity, initial velocity, final velocity, and time and acceleration. So here in rotational motion, we have theta, delta theta, angular displacement, angular velocity initial, angular velocity final, time is same, acceleration is angular acceleration. Okay. So in order to solve this kind of problem, we need to know at least 3 quantities. Okay. If we know 3 quantities, then we can find the rest. And we have these formulas. If it is a uniform motion, that means if there is no acceleration, we use this formula. So V is equal to delta x over delta t. In case of rotational motion, for uniform motion we have omega is equal to delta theta over delta t. For non-uniform motion, which involves speeding up or speeding down or acceleration, we have A is V final minus V initial over t, delta t or t. Here it's alpha is equal to omega final minus omega initial over t. And then delta x is equal to VIT plus 1/2 AT squared. Delta x is equal to V final squared minus V initial squared over 2a. Okay? And you can write the similar equation for rotational motion. For rotational motion, we have delta theta is equal to omega IT plus 1/2 alpha t squared. Delta theta is equal to omega final squared minus omega initial squared over 2 alpha. Okay. So those are the equations we have now. Let's see the question, what the question is asking. The merry-go-round starts from rest, so that means initial velocity of the merry-go-round is 0, omega I is 0. Accelerates at an angular acceleration of 4 meters, 0.4 radian per second squared. So angular acceleration is given, 0.4 radian per second squared, and it accelerates for time of 4 seconds. And then for next 10 seconds, it rotates at constant angular velocity. Okay, so this is for 4 seconds. For next 10 seconds, omega is constant. In other words, there is no acceleration. Okay, and then it decelerates at constant angular acceleration for 6 seconds. So for next 6 seconds, there is deceleration. Deceleration means negative acceleration. So the question is, what is your angular acceleration at 4-second time? So we want to find, what is your angular velocity at 4-second time? So we want to find final velocity at the end of 4 seconds. So let's do this first part. We have three given quantities, and we need to find the other one. So look at these equations and see which one we want to use. We cannot use this one because it's not uniform. Okay, this motion is non-uniform motion, so this is not something we want to use. So which one should we use then? Should we use the first one? Yes, we can use the first one because we have everything here except WF. So alpha is 0.4. Okay, so we want to use this alpha is equal to W final omega initial over T. Alpha is 0.4 radian per second squared. Omega final is what we want to find. Omega initial is 0. Time is 4 seconds. So to get rid of 4 on the bottom here, you can multiply both sides by 4. WF minus 0 is WF. So that means WF is 0.4 times 4 is 1.6. Unit for omega F is radian per second. So that's the first part of the motion. Now second part, for this part, for part B is for the third part actually. So this is A. What is your angular acceleration when it's slowing down to the rest? So we want to find this alpha. So at the end of 4 seconds, your speed is that angular speed, and you will maintain that angular speed throughout this 10 seconds. Okay, so here angular speed is 1.6 radian per second, and it doesn't change because there's no acceleration. And also at the beginning of this part, omega I would be 1.6. Okay, so up to here it's still same velocity, it's not changing, but as it hits this 10 seconds, end of 10 seconds, now it slows down. So this will now go down. So we want to find alpha that slows down the speed, and it slows down until it comes to rest. That means the final velocity, final angular velocity will be 0. So how do we find alpha? So again we can use this equation. So alpha is omega final, which is 0, omega initial, which is 1.6 radian per second, over time is 6 seconds. So negative 1.6 over 6. So that will be negative 0.267 or negative 0.27 radian per second squared. Okay, so that's the deceleration. Now let's look at the third one. How far in meters did it travel? So we want to find the total displacement starting from 0 seconds till this 0 plus 4, 10, 16, by the end of 20 seconds, what would be delta theta, okay, total displacement. So we can find the displacement during this part, find delta theta this part at this part, call that theta 1, and then delta theta during this part, call that delta theta 2, and then delta theta during this part, and then add the 3 displacements, and that will give us the total displacement. So let's first find the displacement during the first part. So which formula should I use to find delta theta here during the first part? We have 2 equations to find delta theta, this one or this one. Should I use the first one or second one? Yeah, you can use either one, I think, because you have everything on the right side. So let's use the second one then. Omega final is 1.6 radian per second squared. Omega initial is 0. 2 times alpha is 0.4 radian per second squared. So delta theta 1, you do the calculation and you get, I think it's 2 radian. Is that 2? 1.6 over 0.8. So what did you get for this one? Huh? 3.2. Okay, 3.2. 3.2. What's the unit for theta? Angle. Theta is angle. Angle is what? Degrees or radian? Radian, yes. We cannot use degree here. Degree only goes with sine, cosine, all those things. Okay. But if you have only theta, then you need to use the radian. So for this part, angular displacement is 3.2. Now let's find for this one. This is uniform motion. For uniform motion, we only have this equation. Okay, we cannot use the 3. The 3 is for one with the acceleration. But here we want to use omega times time. Okay. So I'm just writing this equation in terms of theta. So delta theta is omega times time. So omega is 1.6 radian per second. And then time is, how long is that time? 10 seconds. So that's 16 radian. Okay. Now for the third one, so which one we want to use? So again, we want to find delta theta for this third part. Should I use this one or this one? You can just use the third one. So omega final is 0 because it stops eventually. Omega initial is starting velocity, which is 1.6. And then over 2 alpha. Alpha is negative 0.267. Okay, that's alpha. So do the math and see what you get. So that's 1.6 over 0.435. So what's that number? 4.7. Okay. So total displacement, total angular displacement, delta theta is delta theta 1 plus delta theta 2 plus delta theta 3. So add that, and that. So that would be 20.7, 23. Is that 29.7, 29.2, or 23.9? Is that right? 23.9? Okay. So that's number 3. Let's look at number 4. Okay, a bicycle slows down uniformly from velocity of 8.4 meters per second. Let's see, someone is asking a question here. That's in radian, but the question asks in meters. Oh, okay, that's good. Yeah, thank you for pointing that out. Yes, it's a very good point. So I totally forgot. So this one is in radian. We want to find this in arc length, okay, S. So how much distance will it cover? And we have the relationship between theta and S. So the relationship between this arc length and this theta is S is equal to R delta theta. So we want to find S, so multiply this by R. So R is 4 meters and delta theta is 23.9. So that will give us the distance in meters. Okay. Now let's look at number 4. So the bicycle is slowing down uniformly from the speed of 8.4 meters per second to rest over the distance of 115 meters. Each wheel and tire has an overall diameter of 68 centimeters. Determine the angular velocity of the wheels at the initial instant. The total number of revolutions each wheel rotates before coming to rest, angular acceleration of the wheel, and the time it took to come to stop. So let's start with the first one, part A. So it's asking for the initial velocity. So there are two types of velocities when you deal with angular motion or rotational motion. You can either describe the motion by this angle or distance S. Distance is the arc distance, and this theta is the angular position. Okay. Similarly, you can describe the speed or velocity by using omega for the angular part, or you can also use this velocity v. Okay. This velocity v is how fast it is covering this arc length, and this omega is how fast it is covering this angle. And the relationship between these two quantities is V is equal to omega times R. Okay, that's the relationship between angular velocity and linear velocity. This is called linear velocity or linear speed. This is called angular velocity. So in the question we are given the linear velocity. So Vi is given, initial velocity, which is 8.4 meters per second, and we are asked to find omega I, okay, initial velocity. And we know this relationship. So omega I is Vi over R. So Vi is 8.4 meters per second, and R is the radius of the wheel, which is, we don't have the radius, but we have the diameter. So diameter is 68 centimeters. 68 means it's 0.68 meters, and radius is half of that, so 0.34 meters. So radius 0.34 meters, and you do that calculation, that will give you 24.7 radian per second. Okay. Total number of revolutions each wheel rotates before coming to rest. So the linear displacement is given. We are given S. S is 115 meters. Okay. So it rolls forward, and the total arc length covered is that. And we know the radius of the wheel, which is 0.340. Okay. Now, how many radians it cover during that displacement? So we want to find the angular displacement theta. And once we know the angular displacement, for one revolution it covers 2 pi radian. Okay, one revolution. And if we know how many radians there are, and if we divide that by 2 pi, and that will give us the total number of revolutions. Okay, that's simple arithmetic problem. So find delta theta. How should I find delta theta? Given these two quantities, what should I do to find delta theta? What should I do? Give me the formula. Yes, that's right. So someone answered that correctly. So here we have this formula. S is equal to R times delta theta. So we want to find delta theta. That means S over R. So we want to divide S by R. S is 115 meters. Is that centimeter or meter? Meters. Okay. And then R is 0.340 meters. So that will give us total angular displacement in radian, which is I don't have a number for that. Can you guys figure that, find that out? .338 radian, okay. So that's the total displacement, and in one revolution it makes 2 pi radian displacement. That means number of revolution completed by the wheel is total displacement over displacement in one revolution, which is 2 pi. Okay, so 338 radian over 2 pi radian. So let's see what that is. So divide 338 by 2 pi. Is that 50 point something? 50, 6 divided by 338 divided by 6. That's 53.8, okay. 53.8 revolutions. Okay, that's the angular number of revolutions. So next one, what's the angular acceleration of the wheel? We want to find alpha. And you have two formulas to find that. One is alpha is equal to omega final squared minus omega initial squared over 2 delta theta, and another one is alpha is equal to, or delta theta is equal to v omega I t plus 1/2 alpha t squared. So we have two equations, and you need to decide which one you want to use to find alpha. Should we use the first one? We have omega f, we have omega I, and we have theta. Okay, that means this one we can use. We cannot use this one because time is not given. Okay, time. Okay, so alpha is equal to omega final. So what's the omega final? What is the final velocity of the bicycle? Yes, because it comes to rest eventually. So 0. Initial velocity 24.7 radian per seconds. We found that on part A. That's squared. And then 2 times total displacement, we just found that. Total displacement is 338 radian. Okay, so let's figure that out. Is that negative 0.902 radian per second squared? So that's part C. And then part D, the time it took to come to stop. So we want to find time, T or delta T. We have two formulas that has time. So which formula should we use? We have this formula that has time, and we have A is equal to omega final minus omega initial over time. So should we use the second one or third one? You can use either one, both are fine. So let's use the third one. So this is delta t. Here delta t and t are same, okay? Because delta t is t final minus t initial. Usually we consider initial time to be 0, okay, this to be 0. So that means delta t and t are same, considering the initial time is 0. So sometimes I may be writing t, sometimes delta t, both same thing. So delta t is omega final minus omega initial I'm rearranging the terms here, so that would be alpha. So omega final is 0, omega initial 24.7, and then alpha is, we just found that, negative 0.902. So let's do the math. That'll give you the time. That is, I got 27.4, so you can see if that's the number you get. If you get a different number, please let me know. Okay, now next one, let's look at number 5. So on number 5, we are asked to find moment of inertia of the system that has 4 masses. So the formal definition of moment of inertia is, we talked about this in lab also. So if you have 2 masses connected by some kind of rod, and then you are rotating these 2 masses about this axis. Then the moment of inertia of this system is given by, let's call this one m1, this one m2. This distance from the axis is r1. The distance of this one from the axis is r2. So mass of the first particles times its distance from the axis squared plus mass 2 times distance from the axis squared. That's the moment of inertia. Okay. Let's say if you have a third mass somewhere here, then it would be m1 or m3 r3 squared. Okay. So this r is perpendicular distance this is very important, perpendicular distance of the mass from the axis. Okay, so please keep this in mind. This is very important. And if you have more masses, you add just mr squared for each of the masses. Okay. You may have like thousands of particles. For each of the particles, you just add your individual terms. So, on the question, we have 4 particles at the corner of square. And there are different ways you can rotate the system, okay? Meaning you can have different kinds of axes. So here on the picture, the axis passes through the middle line of the square. Okay? So unfortunately, I cannot show. I don't have the camera on today. I cannot show this to the people on the Zoom, but those who are here. So we have 4 particles, okay, and that's the axis. So axis means now I'm rotating this like that, okay. So this is the axis of rotation. If my axis passes through this board, then I would be rotating. Like this, okay. So that's the axis. If my axis is this line, then I would be rotating like that, okay. So the axis is around which you rotate the object. So here in the picture, this is number 5. We have 1, 2, 3, 4 particles, and we are rotating these 4 particles about this axis. So that's the axis of rotation. No, so we have three parts of this question, and for each of the parts we have different axes of rotation. So let's look at A first. There's a typo, it says B, but that's A. So find the moment of inertia of the system about an axis for A, axis through the center of the square, axis through the center of square perpendicular to the plane. Okay. So this is not the axis for the first this question, this part. Okay. So let's talk about this one first. So for A, your axis is passing through the center of this square perpendicular to this plane. This is the plane, it's perpendicular, so that's the axis. Okay? So you're rotating like that. So for this one, so this is our axis. You're imagine that there is a line passing through the center, okay, through the center, and you are rotating this whole thing around that line. Okay. So for that, what is the moment of inertia? Moment of inertia is different for different axes. For this particular axis, let's call this M1, M2, M3, M4. So moment of inertia, let's call that Mi. For M1, mass is M1. What's the distance between, perpendicular distance between this mass and pivot, or this axis of rotation? Perpendicular distance. There is a line going through this point. What's the distance between this and that point? So our axis is here. That's the mass 1. We want to find the perpendicular distance between this line and that mass. You don't need to tell me the answer, just tell me like how you find that. Let's call that R1. Okay, like that. We have second mass M2, R2 squared, M3, R3 squared, M4, R4 squared. So I'm just asking you how to find this distance. That's half of the diagonal, right? So you can find this diagonal, and half of that diagonal would be the distance. Or if you don't want to find the diagonal, you can just find this, use this triangle, this small triangle, this small triangle. So we want to find this hypotenuse. This distance is halfway, so that means it's I think there's a typo here. On the picture it says 0.4 meters side, but on the question it says 0.2, so either you can choose 0.2 or 0.4. So let's say this whole side is 0.4. So then this half would be 0.2, this would be 0.2, and then this distance would be m1 square root of 0.2 squared plus 0.2 squared. Same thing you do here. So mass, all these distances would be same. Okay, so this distance, this distance, this distance, all they are all same, and masses are also same. So you can just write this to be 4 times m r squared because they are all same. So 4 times mass of each is 0.2 kg, and distance between the particle and the axis is 0.2 squared plus 0.2 squared square root. Okay. Basically we have 0.2 here and then 0.2 here. That's what we are finding. So what is that? You guys need to tell me a number. I don't have the answer for that. Is that kilogram meter square? Do you remember from the lab last time what we got during the lab? What's the unit for moment of inertia we got in the lab? Yeah, that's right, kg meter squared. That's right, because it's the product of mass and distance squared, so kg meter squared. So what's that? What's the number you got? 0.0627. Okay, so that's for that axis. Now let's look at part B. Bisecting two opposite sides of the square. Now this would be the axis, that the one I showed in the beginning. So this is the axis that bisects the middle of the square. Okay, so this is our axis of rotation. Now let's find mi for this axis. So mass 1. Now what is the distance between the axis of rotation and the mass? Perpendicular distance between this axis of rotation and mass. This is the axis of rotation. I
got a different answer for.
You got a different answer?
Yeah.
What you got?
0.226.
0.226. Okay. Okay. So either this one or this one. You guys can figure that out. Okay. Did you take the square root? People who are on Zoom, do you guys have answer? Okay, you guys can figure that out. Okay, so this is just doing the math. Now my question is, what's the distance between this mass and the axis of rotation? This is the axis of rotation. So that's the formula for moment of inertia. Here we want to know, we want to figure out the distance. So again, these masses are all same, so I can just write m for all. I'm pulling this m out because they are all same, okay? I can replace these all m masses by m. In some questions, they may be different, but for this one, it's all same. So mass is 0.2 kilogram. So the distance between the first mass and this axis, what's that distance? It's half of the length of the square, which is, if we consider the length to be 0.4, then this will be 0.2 meter. What's the distance between this m2 and that? Again, same thing, so 0.2 meters squared. What's the distance between this m3 and that? Again, it's same. Okay, same distance, half of the distance, half of the length squared. And then R4 is this distance. It's again same, 0.2 meters squared. Okay, so doing the math, you'll get the moment of inertia about that axis. So to simplify this, I can write this as 0.2 kilogram, 0.2, 0.2, 0.2, so that's like just doing 4 times 0.2 squared. So do the math, and that'll give you some number, kilogram meter squared. That's about that axis. Now, part C, that passes to the center of the upper left and lower right spheres. So now our axis is passing through the corners, 2 corners or diagonal. So now this is our axis of rotation. Now we are rotating like this, okay? So this is the axis of rotation. We are rotating like that. So we're rotating like that. So mi is mass 1 r1 squared, mass 2 r2 squared, mass 3 r3 squared, mass 4 r4 squared. All the masses are same again, so let's just pull it out. 2 kilogram, r1 squared plus r2 squared plus r3 squared plus r4 squared, 0.2 kilogram. R1, this is 1. So what's the distance between this mass and axis of rotation? Perpendicular distance between this mass and this axis of rotation. What's the distance? What's the distance between your body and the chair you are sitting on? This particle is exactly on the axis. So what's the distance? What's the distance? So that's the particle, and that's the axis. So what's the distance between this particle and this point? 0? Yeah, it's 0. Because this particle is exactly on this line, that means it's 0. R2, what's the distance between, here we are talking about the perpendicular distance between this particle and this line. So not this distance, it's not perpendicular distance. Not this distance, okay, perpendicular distance. So we already found that. So this is 0.2 squared plus 0.2 squared square root. Okay, that's the diagonal, half of the diagonal. And then what's the distance between the axis and this point? It's again on the axis, so that's 0. And then what's the distance between this particle and this, or perpendicular distance? That's the distance, which is 0.2 squared plus 0.2 squared. By the way, there is a square here. Okay. And do the math, you get the answer. We are out of time, so please complete that, and we'll continue this next time. And let me know if you guys have any question. Oh, by the way, maybe here is the problem. So I didn't square. This is just r. I didn't square here, so I need to square that. Probably that's the reason you got wrong answer. So please do not forget to square. We have a square for r.